This is Dr. Shankaraiah from Department of Physics. So, in last presentations, I have discussed about some topics in Module 4, which is magnetic and superconducting material. Today, I will discuss about origin of magnetization in magnetic materials. So, what is the origin of magnetization? So, yesterday we have discussed in the last presentation. I have discussed about some definitions of magnetic dipole moment, and magnetization, magnetic field, and magnetic induction, and so on and so forth. So we have discussed about magnetization, right? So what is the origin of magnetization? How a material gets magnetized when we place the material in the presence of magnetic field. So the origin of magnetization we are going to discuss in this presentation. So the magnetic properties of solids arise due to electrons undergoing different types of motions in the atoms, which give rise to magnetic dipole moments. And these magnetic dipole moments are responsible for the magnetic properties of materials. So the magnetic properties are the magnetization of a material is coming because of the electrons that are present in atoms, and due to the electrons undergoing different motions. Okay, and because of the electrons undergoing different motions, they produce magnetic dipole moments, and these magnetic dipole moments are the responsible for magnetic properties of the materials. So the magnetization of the material is coming from the magnetic dipole moments, and these magnetic dipole moments are induced due to the different motions of electrons. Okay, in general, the magnetic dipole moments of the atom arises from three sources. Okay? So the magnetic dipole moment that is responsible for the magnetization of a material comes from three sources. Okay, the orbital motion of electron. The first source is orbital motion of electron. The second one is spin of electron and nuclear spin of electron. Okay, so let me just write them. First one is orbital motion of electron. So the first one is orbital motion of electrons. Second one is spin of electrons. And the third one is nuclear spin. Okay. So these are the three sources from which we are going to get the magnetic dipole moment. Okay. So the magnetic dipole moment is coming from three sources. So the origin of magnetization or the magnetic dipole moment is coming from three sources, that are orbital motion of electrons, spin of electrons, and nuclear spin. Okay, so because of these magnetic dipole moment only, the material gets magnetized, right? So the first origin of magnetization is from orbital motion of electron. Okay, so what is this orbital motion of electrons? The atom of any material consists of a central nucleus, right? Any material consists of atoms, and each atom of any material consists of nucleus as well as electrons that move around the nucleus in circular orbits, right? So you have a material consists of many atoms. Each atom has a nucleus which is positively charged, and electrons that are revolving around this nucleus in circular orbits. You can have different orbits. You have s orbital, p orbital, d orbital. So you have different orbitals. So the electrons are revolving around this positive nucleus in circular orbitals. Each electron orbit is equivalent to a tiny current loop and behaves as an elementary magnet having a magnetic dipole moment. Okay. So this circular orbit, each of these circular orbit act as a tiny current loop, right? So we know that current carrying, any closed loop of current carrying conductor generates a magnetic field, right? So here I have a circular orbital, for example, and in this circular orbital, electron is moving. The motion of electrons is nothing but a current. So this tiny loop, this orbital act as tiny current loop, and because of this current is current is moving, electrons are moving in this closed loop, it generates magnetic moment, magnetic dipole moment. Okay, so this tiny current loop acts as a magnet. Okay, it acts as small magnet and which generates this dipole magnetic moment. Okay, so the total orbital magnetic moment on atom is the sum of orbital magnetic moments of each individual electrons. Okay, so the magnetic dipole moment coming from the orbital motion of electron, because each orbital is like a tiny current loop and electrons are moving in the circular orbits and it is acting as a tiny current loop, and so we know, we have studied already that current carrying conductor generates magnetic field or magnetic flux lines, and because of this tiny current loop it acts as a magnet, elementary magnet having some magnetic dipole moment. And the total magnetic moment of an atom is the sum of all the orbital magnetic moments of individual electrons. Okay, so this is the first source of magnetization of a material, which is coming from the orbital motion of electrons. Okay, so let us go to the next source, which is spin of electrons. So the spin of electron or electron spin, each electron is spinning about an axis through itself, and this spin also gives rise to a magnetic dipole moment. So the first one is because of the orbital motion of electron. Each orbital acts as a tiny current loop and it acts as elementary magnet having some magnetic moment. Right. So that's the first source of magnetization. And the second source of magnetization is spin of electron. Each electron, when the electron is moving in the circular orbit around this positive nucleus, the electron is also spinning itself. The electron is also spinning itself and then it is revolving around this nucleus in circular orbit. Okay, so because of the spin of electron, okay, each electron is spinning about an axis through itself. Okay, so that spinning is also gives rise to a magnetic dipole moment. Okay, so this is the second source of magnetization, and the third source is nuclear spin. In addition to electronic contribution, nuclear spin also contributes to magnetic moment of atoms. Okay, not only this magnetic dipole moment is coming not only from electronic contribution, but also there is a contribution that is coming from nuclear spin, right? So the magnetic moment coming from the nucleus is about 1 by 2000 of the magnetic moment of electron. So the magnetic moment that is coming from nuclear spin is very small. So generally when we study the magnetic properties of solids, we generally neglect this magnetic moment coming from nuclear spin because it is very small. It is 1 by 2000 of the magnetic moment of electron. So it's very small. So in general, the resulting magnetic moment of an atom is the sum of orbital magnetic moment and spin of magnetic moment of electron. So in general, when we study the magnetic properties of any material, we just take the contribution of magnetic moment coming from electrons, because the magnetic dipole moment coming from nuclear spin is very small compared to the magnetic dipole moment coming from electrons. So now we have discussed the origin of magnetization, or what are the sources that gives rise to the magnetization of a material, and we have learned that there are three sources that are responsible for the magnetization of a material, and the three sources of orbital motion of electron and electron spin and nuclear spin. So let us understand how do we get the magnetic dipole moment coming from the orbital motion of electron. Okay, the quantitative derivation of magnetic moment coming from orbital motion of electron. So I am denoting this magnetic dipole moment coming from orbital motion of electron by mu l. So let us consider an electron of charge E revolving around a nucleus in time period t. Okay, so in a circular orbit of radius r. So I am saying that there is a I'm considering that electron of charge E. So there is an electron of charge E. This electron is revolving around the nucleus in time period t in a circular orbit of radius r. So this is a circular orbit, and the radius of this circular orbit is r, and the electron is having subcharge E. Okay, electron is having subcharge E, and this electron is moving in around this circular orbit of radius r in time period t. Okay. So then a magnitude of circular current is given by. So because of this, electron is moving around this nucleus in this circular orbit of radius r, it is going to produce a current. Okay, and the magnitude of this current is given by this. I is equal to charge by time. The charge of electron is E, and the time period it is going to revolve complete one revolution is t. So I, the circular current that is coming from the orbital motion of electron, is E, charge of electron, divided by the time that is taken to complete one revolution, it is t. So the circular current I is equal to E by t, charge by time. Okay, so where t is the time period, so you can write this time period in terms of angular frequency, which is 2 pi by omega. Okay, so now you can substitute this t in this equation. So if you substitute this t in this equation, so E by 2 pi by omega, or E omega by 2 pi. So this is the current, the magnitude of the current that is produced because of the orbital motion of electron. Okay, so current equation, that the magnitude of the current that is produced is E omega by 2 pi. Okay, so the magnetic moment, dipole moment of electron is mu L, which is equal to current multiplied by area. The amount of current that is produced multiplied by the area of this circular orbit will give us the magnetic moment produced by the orbital motion of electron. So that is, magnetic moment is current into area. So current multiplied by area. So current is I. We know current, which is E omega by 2 pi. So mu L, the magnetic dipole moment, mu L is equal to E omega by 2 pi, which is current, multiplied by the area of the circular orbit. So the area of the circular orbit is pi r square. Okay, so E omega by 2 pi into pi r square. So this pi will cancel out, and you will get E omega r square by 2. So this is the magnetic moment coming from this orbital motion of electron. So let us understand this magnetic moment a little bit more. Okay, so the magnetic moment coming from the orbital motion of electron is mu L is equal to E omega r square by 2, where r is the radius of this orbit, E is the charge of electron, omega is the angular frequency. We know that angular momentum of any particle. So we know the equation for angular momentum. Angular momentum is denoted by A. Angular momentum L is equal to R cross P. Okay, so P is momentum, and you know the equation for momentum. Momentum is mass multiplied with velocity. So R into m into v, because momentum P is equal to m into v. Okay, so you can write angular velocity as v is equal to r into omega. Okay, so angular velocity v is equal to r into omega. So if I substitute v in the place of v as r omega, so then m r into r square and omega. So m omega r square. So that is why I have here m omega r square. So I have just written the angular momentum equation. L is equal to r cross p, where p is momentum. So I have replaced the momentum by m into v, mass into velocity, and I have written velocity in terms of r omega, angular frequency. So then I got m omega r square. Okay, very good. Okay, now the magnetic moment of electron we have derived, which is E omega r square by 2. Now I am going to write this equation in terms of angular momentum. Okay, so then the angular momentum is, I am going to write this equation. So I have E omega r square, but here I have L in terms of L. So if I want m in the numerator, I should divide by m. So there is a m here. So then I have m omega r square. So there will be E L. Okay, so mu L is equal to E L by 2 into L. Okay, so you can have plus or minus you based on clockwise direction or anti-clockwise direction. So based on the, if it is clockwise direction, you can take as EL by 2m, or if it is anti-clockwise direction, you can take EL by minus EL by 2m. So the magnetic moment that is coming from the orbital motion of electron is EL by 2m. So you can take plus or minus. So this is the equation for the magnetic moment coming from the orbital motion of electron. So we have written in terms of the angular momentum of this electron. So EL by 2m, where L is orbital angular momentum of an electron. But from Bohr's atomic model, okay, we know Niels Bohr model for atoms. So from Bohr's atomic model, L is R cross P, which is mv, or P is momentum, so mv into R. So this angular momentum must be an integral multiples of h by 2 pi. Okay, so if you remember this Bohr's atomic model, we know that the angular momentum L is equal to n into h cut, or n into h by 2 pi, where n is integer. So the angular momentum is integral multiples or integer multiples of h by 2 pi. So whatever equation we have derived here, which is E minus EL by 2 pi, must be, so this L must be equal to NH by 2 pi. So here I am going to replace N by L, where L is orbital quantum number. So LH by 2 pi. Okay. So whatever we have here, so mu L is equal to minus EL by 2m. So I can take plus or minus. So anyway, I am just using minus here. So EM by 2 pi and L is actually equal to LH by 2 pi. So I am going to replace this angular momentum L equation LH by 2 pi. So E by 2m into LH by 2 pi. So that will be, so yeah, so anything, yeah, EH by 4 pi m. So 2 into 2, 4 5 m. So EH by 4 pi m into m. So this is the magnetic moment coming from the orbital motion of electron, which is mu L is equal to EH by 4 pi m into L. So the sign is based on the electron motion, clockwise motion or anti-clockwise motion in this circular orbital. Okay. So where EH by 2 pi, I am defining this term EH by 2 pi m, EH by 4 pi m, sorry, EH by 4 pi m as mu B, which is called as Bohr magneton. Okay. So Bohr magneton is the unit of magnetic moment. So it is clear from the equation that electron can take only certain specified values of magnetic moment depending on the value of L. Okay. So electron can take only certain values of magnetic moment depending on L, whether L is 1, 0 or 2. Depending on the value of L, electron is going to take only certain values of the magnetic moment mu L. Okay. Fine. So we have, so the magnetic moment coming from the orbital motion of electron mu L is equal to mu B into L. Mu B plus or minus mu B into L. So where mu B is the Bohr magneton, which is equal to EH by 4 pi m. Okay. So we have derived the equation for the magnetic dipole moment coming from the orbital motion of electron. And we find out that this magnetic dipole moment coming from orbital motion of electron can take only certain specified values based on the value of L. Okay. So that is the first source of magnetization of a material, which is orbital motion of electron. There. The second origin or source of magnetization is coming from the spin of electron. So I am denoting this by mu s. So the magnetic dipole moment coming from the spin of electrons is mu s. According to quantum theory, electrons should have intrinsic angular momentum due to spin. Okay. Because of the spin of electron, they are going to have intrinsic angular momentum. Okay. And spin is also quantized both in magnitude and direction, and it can take only one value, that is plus or minus half. Okay. So as per quantum theory, electrons should have their intrinsic angular momentum due to spin, so they can, based on their clockwise or anti-clockwise direction. So along about an axis, whether the electron is revolving in clockwise or anti-clockwise direction. So based on the orientation or rotation of this electron about its axis, it can have only quantized, the value of its spin is quantized, it is either can be plus of or minus of. Okay. So the magnetic moment produced due to spin of electrons is called spin magnetic moment mu s, and it is equal to plus or minus mu b. Okay. So the magnetic moment that is coming from the spin of electrons is denoted by mu s, and as per quantum theory, electron spin is quantized both in direction and magnitude, and it can take only two values, plus or minus half. Okay, so that is the reason why the magnetic moment produced due to the spin of electrons is called spin magnetic moment, and it can take only two values, plus or minus mu b. Okay, so n spin magnetic moment of electron is equal to mu b, and that is 1 Bohr magneton. We know that the value of Bohr magneton mu b is equal to Eh by 4 pi m. Okay, so Eh by 4 pi m. So this is the second source of magnetization coming from the spin of electrons, which is equal to plus or minus mu b. When we derive the magnetic dipole moment coming from orbital motion, that is plus or minus mu b into L. So that is from orbital motion of electrons, and this is spin off because of the spin of electrons. Okay, so yeah, so this is like orbital motion of electron, but electron can rotate about its axis itself, so that is spinning of electron. Okay, so and it is also quantized as by quantum theory, and it can have its both direction and magnitude is quantized. It has only plus or minus half, and that is the reason why we have plus or minus mu b. Okay, so the magnetic moment, spin magnetic moment, is equal to 1 Bohr magneton. So the third source of magnetization is due to spin of electron, nuclear spin, which is denoted by mu n. Okay, the magnetic moment coming from nuclear spin is denoted by mu n, which is equal to Eh by 4 pi mp. So the magnetic moment, magnetic dipole moment due to spin of nucleus is given by mu n, which is equal to Eh by 4 pi mp. Okay, where mp is the mass of the proton and mn is the nuclear magneton. So mu n is the nuclear magneton and mp is the mass of proton. So here the new magnetic moment is coming from nucleus. Okay, so and that is the reason why we are using here in the place of m, we are using mass of proton, and this mu n is nuclear magneton. So when we discussed about this magnetic dipole moment coming from electron, we mentioned that mu as Bohr magneton, and here the magnetic dipole moment coming from the nuclear spin, we are denoting it by mu n, and we are calling it as nuclear magneton. And the value of mu n is 5 into 10 power minus 27 ampere meter square. And we know that the magnetic dipole moment coming from nuclear spin is very, very small. Okay. So the major contribution to atomic dipole magnetic moments comes from the spin of unpaired valence electrons. That is what we have discussed. And the number of such magnetic moments may align themselves in different directions to generate a net non-zero magnetic moment. Okay, all this a major contribution is coming from the electrons, okay, unpaired valence electrons, and a number of such magnetic moments may align themselves. If these magnetic moments can align in single direction, in one direction, then they are going to produce non-zero magnetic moment. So if they are oriented in the same direction, we are going to sum up all these magnetic moments, and then we will get a non-zero magnetic moment. Okay. When the substance is placed in a magnetic field, the atomic dipoles are aligned with the directions of magnetic moment along the direction of external field. Thus, the material is magnetized. When we place the material in the presence of a magnetic field, all these magnetic dipole moments are oriented in the direction of magnetic field, and hence the material gets magnetized. That means there is a non-zero magnetization produced because all the magnetic moments are oriented in the direction of magnetic field, and when you sum up all these magnetic moments, you are going to get non-zero value, and hence the material is going to get magnetized when we place the material in the presence of magnetic field. Okay. So what is Bohr magneton? It is the elementary electron magnetic moment. Bohr magneton is an elementary electron magnetic moment. It is elementary in the sense that no electron can have a magnetic moment below it. This is the smallest unit of magnetization. So this is any electron is not going to have a magnetic moment less than the Bohr magneton, right? So it is the natural unit for the measurement of atomic magnetic moment, and it is denoted by mu b. So we know that Bohr magneton mu b is equal to Eh by 4 pi m, and the value of this is 9.28 into 10 power minus 24 ampere meter square. Okay, so we know that this is coming from electrons, orbital motion of electron and spin of electron. So in both of the electronic contribution to magnetic moment, we are going to have this Bohr magneton. And when we discuss about the magnetic moment coming from nuclear spin, it is very small. It is around 10 power minus 27. So that is the reason why when we discuss or when we study the magnetic properties of materials, we are going to neglect the magnetic dipole moment coming from nuclear spin. We are going to consider only the magnetic dipole moment coming from electronic contributions. Okay, so these are some of the references that I used in this presentation. And to summarize, in this presentation, I have discussed about the origin of magnetization, right? So I have discussed about origin of magnetization. That means how a material gets magnetized when we place the material in the presence of magnetic field. So then I have discussed the origin or the sources. I discussed that there are three sources. Okay, so the sources of magnetization, right? There are three sources. There are three sources because of which a material gets magnetized. Okay, so the first one is orbital motion of electron. Orbital motion of electrons, and the second one is spin of electrons. The third one is nuclear spin. These are the three sources from which a material gets magnetized when we place it in the presence of magnetic field. Okay, and then we have derived the magnetic moment coming from the orbital motion of electrons, so which is mu L is equal to plus or minus mu B into L, where mu B is the Bohr magneton and mu B is equal to Eh by 4 pi m. And we have also derived the magnetic moment coming from the spin of electron, which is plus or minus mu S, which are plus or minus mu B, right? So that is also equal to 1 Bohr magneton. And the nuclear spin coming from a nuclear spin, the magnetic moment coming from nuclear spin is mu N, which is equal to Eh by 4 pi m. And we have also discussed that Bohr magneton is the smallest magnetic moment an electron can have. That is the smallest magnetic moment. Any electron cannot have a magnetic moment less than the Bohr magneton. Okay, so yeah, so I'm going to end this presentation here, and in the next presentation we will discuss about the other topic in magnetic materials. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.